Okay, what we're going to do is we're going to do a problem dealing with density and the ideal gas law. So the original ideal gas law is the following equation: PV equals nRT. And so what we're going to do is we're going to find density, or use the density equation by manipulating this ideal gas law into where we have mass and molar mass. And to do that, we substitute in for N, which is moles. We're going to substitute in for that. N equals the mass of a gas divided by its molecular mass, and that'll get us moles. So what we do is we substitute that in for N. And then what that equation becomes now is PV equals little m RT over capital M, which is our molecular mass. So then what we can do is, now we have mass and volume, and when we take mass divided by volume, we'll get density. So we're going to continue to work with this equation, which again is PV equals little m RT over capital M. So when we switch this around, we're going to divide both sides by V. That will cancel out the volume on the left side. And then we've got three variables, R, T, and capital M, that are on the right side of the equation, and we want to just leave it as M over V. So the next thing what we're going to do, so that we don't have a lot going on in that one setup to where I'm continually changing it around, we'll show it like that. Then what we're going to do is multiply both sides by capital M. And then we're going to divide both sides by RT. So then, when we rewrite this, density is equal to mass over volume, which is D equals MP over RT. So that's what we're going to use to solve the problem above. It says the density of a gas was measured at 1.5 atmospheres, 27 degrees Celsius, and found to be 1.95 grams per liter. That's the density. What we want to do is calculate the molar mass of this. Okay? So we're going to use this equation here, and we're going to isolate capital M. So again, we're going to manipulate the variables. We're going to divide both sides by P, and then we're going to multiply both sides by RT. And when we do that, we get dRT over capital P, pressure, equals molar mass. So that's the equation we're going to use in which to solve that original setup that we have right here. Okay? So I'm going to go ahead and erase the information down below. So that we have this all on this same page. And then what we're going to do is we're going to take that original equation, that's D equals, I'm sorry, we won't do D. We're not trying to find density. But what we're going to do is we're going to use capital M equals dRT over P. So D equals 1.95 grams per liter. Our R is based upon our pressure. Our pressure is in the atmosphere, so the constant, ideal gas law constant for that is 0.08206. And the units for that, if we want to have those all in there, we won't. I guess we won't need them. We could put them in there if we wanted to. We've already seen some of that before. The temperature is degrees Celsius plus 273, so it'd be 300 Kelvin. And then the pressure is 1.5 atmospheres. Okay, so we have everything we need. So we're going to go ahead and put in the 1.95 grams per liter. We're going to go ahead and put the R is 0.08206. And then the temperature is 300 Kelvin. And I'm running out of room here, so put it in really, really small. So that's supposed to be 300 Kelvin. And then we're going to divide by 1.5 atmospheres. And when we do all the calculations for that, M equals 32 grams per mole would be our units. And if you had to try to figure out which one, what kind of molecule that would be, or what type of gas that would be, if you look at O2, that's 32 grams per mole. Okay? So that's one setup. The other setup that you're going to have to know how to do deals with Boyle's law and looking at Dalton's law of partial pressures. So the second type of problem that we're going to do deals with, again, looking at Boyle's law, which says P1 times V1 equals P2 times V2, keeping temperature and pressure constant. The other one is Dalton's law of partial pressure. It says the P total equals P1 plus P2, and so on and so forth, depending upon how many gases you have in a sample. You can add them all, their partial pressures together, and get the answer. So I'm going to go ahead and do a drawing on this next page. And what we have is we have a cylinder that has a gas in it. It's connected to a larger cylinder that has a gas in it, and there's a valve that is closed and allowing the two gases to not combine at this point in time. So this one, make it easy, we're going to make this pressure inside of this container. We'll say that this is gas A, and this one's gas B. Okay? And then, we'll say this is a pressure of 2 atmospheres, and the volume of it we'll say is 1.5 liters. And then this gas we'll say is taking up a bigger volume. Oh, we'll say it's 2.2 liters. And then we'll go ahead and say that the pressure inside this one is 1 atmosphere. Okay, so we're just making up a gas and putting it in there. Alright, so keep that in mind. We have 2 different gases, gas A and gas B. And what we're going to do is we're going to release this valve and allow them to combine. And then what we want to know is the final pressure in both flasks combined. Okay, so we want to know the final pressure. So here we're going to do, we're going to go ahead and open up the valve so that now they're going to combine and mix together. And they do that spontaneously through a process called diffusion. So the way you would solve this is gas A was under initial pressure P1 of 2. Initial volume of 1.5 liters. Now its final volume is going to be the 1.5 and the 2.2 liters combined. So that would be a total of 3.7 liters would be the new volume. Okay, so what we'll do is we'll take P1 and V1 equals P2 and V2. We want to know the new pressure of A, gas A. So when you look at it, we had beginning pressure was 2 atmospheres of gas A. It had a volume of 1.5 liters. The ending pressure we want to know. That would be the partial pressure of gas A. And then the final volume would be 3.7 liters. So 3.7. So then we solve for P2, which would be pressure of A gas. So it would be 2 atmospheres times 1.5 liters divided by 3.7 liters. And then that would give us an answer for the partial pressure, which would be basically 3 divided by 3.7. Which would be 0.81 atmospheres. Okay, we'll keep that in mind. We'll do the same with the other one, where we started out with 2.2 liters and 1 atmosphere, so that would be our beginning pressure, beginning volume of gas A. So 2.2 and 1 atmosphere. 2.2 liters. Okay, times 1 atmosphere. Okay, and then what we're going to do is set that up to the pressure of gas B times, again, the same volume would be 3.7. So then we would take 2.2 liters times 1 atmosphere divided by 3.7 liters. Liters cancel out, and the atmosphere is the partial pressure of gas B. And that answer is 0.595, so we'll make that 0.60. Okay, so then if we want to know the total pressure inside that flask, we take Dalton's law of partial pressure. It says P total will equal the 2 partial pressures. So the first one that we had, where we went ahead and did the work, that wasn't the one we wanted. That was our equations. There's our setup. Okay. So there was gas A, which is 0.81 atmospheres. .81 atmospheres, and then that would be added to the 0.60 atmospheres, and so we'd end up with 1.41 atmospheres. atmospheres. And so what we do is we take a look at the two partial pressures, gas A and B, we add them together, and that gives us the pressure inside these two containers once they're combined. Okay? Any questions? That's kind of what the pressure is going to be. It's going to be between 2 and 1. So I need to make sure that the original assignment I gave you on Monday, we're going to add to it. And in your book, you're going to go ahead and do the following two added on to that assignment. You're going to do problem number 79 on page 237. And problem 85 on page 238.